Alright, are there markers in here somewhere? Yes. So, let's talk about 3 more. So I'm going to show a different example. I know he showed one in class of an NFA. I don't remember which one, but he said that this one would be disjoint with it. So what about, let's say I have some language, some DFA accepting L1, or NFA, doesn't really matter. I have a machine accepting L1, and I want to now accept the language of all strings X. So I'm going to define an L2 that I want to build a machine for. I should write this bigger. Have some L. That's off the screen. Okay. I want to define an L2 such that X is in L2. If, I don't know if you guys are familiar with this notation, but so some string X is going to be in L2 if, let's see, if X equals Y to some constant where Y is in L1. Does this notation make sense? So basically, let's say you have some string Y, but now it's going to be repeated some arbitrary number of times. So basically, like I could have, if this language was the language of, you know, if it just had 0, 1, 0, and 1, 1 in it, then this would accept every string, like it would accept strings like this. It would accept 0, 1, 0, 0, 1, 0, 0, 1, 0, but it wouldn't accept 0, 1, 0, 1, 1, right? Because that's 2 different strings from the language concatenated together. This accepts 1 string from this language concatenated together some arbitrary number of times. Does that make sense? So, let's see. So what are people's thoughts on how we could build an NFA for this?
I think the thing that confuses me about building like an NFA or DFA based off of another one is how do you like I think that's just like my main like confusion, like how do you like given some like Q or whatever that you don't necessarily know like what's exactly in Q. Like how do you like use that to like create a new Q and stuff like that?
There's nothing problematic about it. The problem intuitively that I think makes it hard for people is that unlike the NFAs and unlike other like NFAs and DFAs, especially DFAs, you can't draw it and look at it and understand it.
Yeah, that's
right?
my problem.
It's hard to get intuition about it because you can only talk about it somewhat abstractly. So.
Wait, I don't know if this is allowed, but like, could you change the original final accepting state and like have another thing that goes back to the beginning, and then also have like an epsilon out of the final accepting state to some like new accepting state?
So, if you epsilon back to the beginning from an accept state, notice then you would accept something like 0, 1, 0, 1, 1, right? Because I would get to the accept state for this in L1.
Yeah.
I would epsilon back, and this would still be an accept
Okay,
state.
so like no epsilons, it's like just another.
You'll still need an epsilon transition, but they'll need to take you out of L1.
Okay.
And I think basically you're just going to use a bunch of copies of L1 to define L2. And this is almost always how you're going to handle these sorts of situations where I tell you like you have, L1 and L2 and you want to build L3. Well then, literally all you can ever do is use copies of L1 and L2. And you're allowed to use many, many copies of them. In fact, you're allowed to use an undetermined number of copies of them, right? Because when I tell you L1, if you think about it abstractly, I don't need to tell you it accepts these strings. I'm just going to tell you it's an arbitrary language L1 accepted by a DFA. There exists a DFA that accepts it. Well, what I can do is let's see. What's the best way to put this? acceptable by? I'm trying to think. This is counting. Let's say L1 accepts a finite number of strings to make this a nice problem to work with. I don't even want to think about the case where L1 could be infinite. Anyways, so L1 accepts some finite. If L1 accepts some finite number of strings, then what we do is build like an extra large DFA for L1 that has a separate accept state for each string it originally accepted, right? It's finite, so we can just make, if it accepts a finite number of strings, then we could just use a finite number of states to have an accepting state that's separate for each one. So like there'd be one accept state, let's say Q4 for this one, and some accept state Q7 for this one, you know. And so I'm gonna at some point separate all of these in the machine.
Are you like sort of like enumerating all of the different like possibilities of what you can get?
Yes.
And then just like
You can think of it like a tree. If you really want to go super extra in a machine, you can just do this, right? Start state, 0, 1. And you can just keep doing this, doubling the number of states you have at every step, right? And so let's say that if there's a finite number of strings, so here's probably the easiest way to think about it, where you could explicitly construct it. Though you'd be making a lot more states than you need to, but that's not a problem. So if L1 accepts a finite number of strings, then there exists a string that has the longest length among strings L1 accepts, right? Well then, after we're doing this process, let's say the length is n, okay? Then after n transitions, and doubling the number of states every time, you will have an accept state for every single string accepted by L1 that are distinct from one another. Right? Because every different string leads you to a different place, because for every possibility I've made a new state, and so then I just make some of them accept states, and we're done. Okay, so I've made a separate accept state for each string this accepts because it accepts a finite number of strings. Does that make sense? So now that I've done that, what I can do is I can epsilon transition out of all the accept states of this, and for each one, I actually need to go to a different DFA, because I don't want to accept things like this. So if I epsilon transition out of the accept state for 1, 1, I now want to epsilon transition to a DFA for this, that the only accept state for it is 1, 1, and from there it epsilon transitions back. Here, I'll give a exact example. So one of the accept states of this machine would be here, right? 1, 1. From here, I'm going to epsilon transition. So it might have other accept states. Where's the other one? It's going to be a little deeper in the tree. Give me a sec. 0, and then, this one's going to be 0, and then here, and then there's another 0. Transition, no, this isn't the way to do it. It's over here. Okay, right, there's another accept state there, right? But what I'm going to do is I'm actually going to epsilon transition this to a new version of this, another copy of this DFA, where the only accept state is this one, and it epsilon transitions. Oh, that's off the top, isn't it? Whatever. Give me a sec. I'm just going to lower it down a little bit. I'll draw it a little bigger. So, this is an accept state, and epsilon transitions back to there. And then, it did before have this path, 0, 1, 0, that led to an accept state, right? But I don't want that to be an accept state anymore. Why?
Wait, can you explain the epsilon back?
Sure. The epsilon back is because this language is going to accept any string that is a concatenation of some string in L1 some number of times.
Oh, so you have 1, 1, and then it epsilons 2, and then 1, 1, and then so that's accepted because it's 2 1, 1. So then it goes, but why does it go back?
It goes back because it could be 1 1 1 1 1 1.
So that part doesn't enable the repetition.
Because that part can repeat as many times as you want.
And then you don't want that to be an except because then it's not the repetition.
Exactly. It's not a repetition of the first thing you saw. So once you've seen the first except state, once you've seen, let's say the first string, like once I've here, I'm like, okay, so I'm looking for repetitions of 1 1. So I transition you to the machine specifically built to look for repetitions of 1 1. Does that make sense? And now, so let's say if there were 100 things this L1 accepts, I would need 101 varieties of L1 to do it, right? So this is an example where I could have defined L1 abstractly as just some language that accepts a finite number of strings, and you could have kind of informally described how to do this process, right? The informal way to do all of this would be to say, you build this machine and you assert, well, there's going to be a separate accept state for everything because I'm just enumerating all the possibilities up to the maximum size of a string this accepts, right?
Yep.
Then I transition, each of those transitions to a separate copy of this DFA, where the only accept state now is the accept state you came from, you epsilon transition from. And you add an epsilon transition from that accepting state back to the start of this submachine.
So for problem 3,
Mhm.
if that original accept state
Mhm.
there
Mhm.
was actually if the copy original starting state, if those are the same, then you would never mind.
But this is what I did, right? So I wanted to remember something, right? So one of the main problems of question 3 is that you need to remember what state you came from, right?
Does that mean you have to like just put the epsilon in the right place?
So, well, the epsilon goes to the start state of L2 for question 3, right?
Mm-hmm.
But then when you epsilon out,
Yeah.
where do you go in this,
So it's that's the problem.
Yeah, and so if you can think about whether additional copies of L2 might assist you in solving this issue, right? Because one of the problems of epsiloning multiple states to L2 to one L2 is you forget where you came from. And so something like this might work, where you epsilon to, you make additional copies of something because you want to remember something about it. That's generally the way to solve these sorts of problems in DFAs and NFAs, is like, I want to go to this machine, like I want to epsilon transition to somewhere, but I need to remember some auxiliary information about it. Then I'm just going to make copies of it for each possibility for the auxiliary information. Does that make sense? Like a counter. If I have a counter that could range from 0 to 9, I'm going to make 9 copies of my NFA, or wherever I'm transitioning to, each one of which is associated with the state of the counter. Because that's kind of the only way to remember things in these machines. Does that make sense?
Yeah, makes sense.
Okay. Cool. But we started early because she has a conflict in time, but I was discussing roughly question 3, and I was going quite fast because we discussed some of this earlier, but we can now go back 10 steps and make this parsable for you guys. Okay, so do you guys have questions about question 3? Where did you guys kind of get? Like, what do you guys already kind of know about?
I sort of modeled it after the one in the lecture about concatenating 2 languages.
I see.
So that's what I started from. And then I sort of ran into that problem where it's like once you get to like a word in L2, you finish the word every time, but then you don't know how to get back.
Exactly. No problem. Have a good one.
Like from every letter in L1, you just epsilon transition to the start of L2 though, right? Like that's how you get all the variations.
Yes. Yeah.
Okay.
So
then for each one, you need to know how to get back to that
Right.
respective.
And does this kind of maybe give you an
This
idea?
makes a little sense, but
So,
how would you
so
like...
first I can describe what's up here first, because I know you missed where I was defining these languages. Basically, L1 is some arbitrary language that accepts only a finite number of strings, let's say. And L2 is the language that accepts all strings that are repetitions of any string accepted by L1. But the repetition.
What's the
it's a C. It's for some constant
okay,
C.
Sure. Okay.
Like it's definitely going to be constant because strings are a finite size. Like any input's going to have a finite size, right? But this is arbitrary. Basically, it accepts like y star for any y in L1.
Okay.
Yeah.
So like, what's the way that you would like?
That's actually a better way to say it. It accepts, x star. Oh, but then I have to make the you know what? I'm gonna leave it as it was. Let's say the constant is. So it's sort of annoying thing, because I've put any constant or like if you put x star, 0 is always a possibility, so you have to add an except state here. Right? Because star can be nothing, no copies of it. So no matter what this language is, the empty string would be accepted by this. Anyways, that's just a technical point. So x star, where this is a much cleaner way to put it, for x in L1. Right? So what I did is, because there's a finite number of strings accepted by this, just by assumption, I build and I know there's a DFA that accepts it. I build a DFA, actually for any language that accepts only a finite number of strings, there exists a DFA for it. You can think about that if you want, but actually this is basically the reason that's true, which is that if this accepts a finite number of strings, then there exists a longest string it accepts. In which case I can enumerate all possible paths out to that length, right? And then make a separate accept state for each string. Because this tree enumerates all possible strings of out to the maximum length of thing this accepts. And then you make like a trap state at the end. So like if you reach your maximum length, everything goes to some state they can't leave. Does that make sense? So that it doesn't accept. But basically, you go out to that point and you make an accept state everything that you want to accept. And that's it. But the reason this is important is because it gives me a separate accept state for each of these strings.
So it's like a unique machine, or like
it's you might be able to make a more elegant machine that accepts this.
Or wait, are you talking about like the epsilon so like this epsilon transition to this machine?
I'm not even talking about the epsilon yet.
Okay.
I'm ignoring the epsilon. I'm just talking about this tree.
Okay.
I'm talking about the machine for L1. So this whole thing is just meant to be L1. Me accepting L1. So here though, notice I have a different accept state for every string accepted by the language. So in this case I was using as an example, the language that accepts 0, 1, 0 and 1, 1. So I would want to accept things like 1, 1, 1, 1, 1, like 6 ones, right? I would want to accept that. But I wouldn't want to accept this string, right? Because it's a concatenation of two different strings in the language.
Isn't 6 ones just a concatenation of...
Yes, 6 ones is fine. We accept 6 ones. We don't accept this string, 0, 1, 0, 1,
Oh,
1.
because that isn't a concatenation of...
It's not a concatenation of the same thing, right? It's a concatenation of two different things from the language.
Oh, got
But I want to pick one of them and concatenate it any number of times.
Okay.
Does that make sense?
Yes.
Great. So that's why I want a separate accept state for each of these strings. Because now what I'm going to do is, let's say that
For
I want
any number.
Yeah. So for 1, 1, I want to epsilon transition to a modified version of the L1 machine. Which is to say that it's the same as the L1 machine, except that it doesn't really matter if this is an accept state or not, actually. It can be a copy of the L1 machine, except that, whatever, I'm just going to remove it, because I think it's the description simple. Well, it doesn't matter because, this is an accept state. So if you got to here,
Then it accepts.
yeah, and this is an accept state. So the only ways to get here are epsilons from accept
So what
states.
is that machine doing?
This machine is going to check for repetitions of the initially noticed accepting string. So let's say that this first L1 machine detects 1, 1 in there. Now, this NFA is going to check if the string is any number of repetitions of 1, 1.
Okay, and
Right.
this is like L2?
This is L1. It's a modified L1.
Okay.
But I notice I don't need to know anything really about L1 to build it informally.
Mm-hmm.
Right? I can just say this is a copy of L1, except that I remove all the accept states except for the one at 1, 1. And then I add an epsilon transition from this accept state back to the start state of this submachine.
But what if you like from those 2 ones, like what if you had like more ones after that?
So after those, so let's say, if I had 6 ones, which
Yeah.
I should accept, right?
Yeah.
Let's see if this accepts. I have to keep writing stuff off the board. I'm sorry, guys. Give me a sec. Let's see the accepting of this, right? Okay, so the first 2 ones get you here,
Mhm.
right? Then we epsilon transition to here.
Mhm.
You don't have to epsilon transition, but I'm just gonna follow the one path that does happen to accept,
Mhm.
right? Like some of the paths, there's an extra branch that might end up here, but let's just ignore that for now. Does that seem fair?
Yeah.
So 1, 1, then I'm gonna take this epsilon transition, go 1, 1,
Mhm.
take this epsilon transition,
Yeah.
1, 1.
Oh. Okay.
Right, but the reason I got rid of this accept state is because I've already seen 1, 1
Uh-huh.
and epsilon here,
Right.
and so I don't want to now accept 0, 1, 0 concatenated
Right.
to it.
Yeah, 'cause we don't want that.
But I do want to accept any number of concatenations of this, so I make an accept state here and transition back to its own beginning.
Oh.
And I can do this once.
As
I
many
can
times as you want.
yeah, and I can build a machine like this for each accept state in the original machine.
Right.
So I'll build another one coming from here,
Mhm.
going to a similar machine, except it's going to have its accept state here, and its epsilon transition back to the
okay.
start here. Does that
Okay,
make sense?
Yeah, that makes sense.
That makes
Yeah.
So notice, I needed to remember something. I needed to remember what is the first string I saw. And to do that, I just made more machines. Just more
Okay.
copies of the machines with slight variations. And this is the sort of thing you can do.
And like when you're defining that, you're like, just take any accept state, and I like, how do you formally like?
So how do you formally and informally write the answer?
Yeah.
Yeah, because you want to do it formally enough that you get all the credit.
Right.
But it is impossible to do it like formally in the way we did formally the DFAs from last assignment because you haven't been given these machines.
Right.
Because we don't know like what
Yeah,
the
yeah.
alphabet is or whatever, right? Or, like,
It doesn't really matter is the important thing. Is that
Can you just sort of give an explanation like why you think it's correct, sort of, or?
yeah, I mean, you can probably prove it's correct, but we don't expect that. I don't.
Okay.
And it's just but let's see. So basically for this one, what would I have done? How would I have formally explained this? I guess I would have said, well, because of the star, I'm always going to, like, I guess I would describe this machine first.
Mhm.
I would say everything I said to you guys, which is like, well, because we know this accepts a finite number of strings, I'm going to build a machine that enumerates all possibilities out to the maximum length of a string accepted by this. And then I'm going to make an accept state, all the states that correspond to strings accepted by this. Does that make sense? This is just a tree that's doubling at every depth, right? It's going to enumerate all possibilities out to that length. And then I build a trap state that everything goes to after that. So let's say the maximum length of something accepted by L1 is n. I keep writing off the board. Is n. Then I'm going to count out to n, and then this will be at like distance n plus 1. And I know that everything that was accepted of length n or less is somewhere in here. And I can just circle them and make them accept states.
do we need to like define like the 5 tuple thing? Like,
No.
Oh, we don't.
I mean, no, because like because you can't even do the full transition function, right? A full transition function requires every
Every like state.
state to be defined. Like it's you.
But you could do like informally, right? And be like, oh well, like for these states.
So you could do it formally in the sense that you could say like all these transitions. You should essentially define them all. Like you should still
so
pay attention to the
expected
tuple.
To sort of come up with this architecture.
Yeah.
And
Because he says informally, you don't have to formally define all these things, but you do need, given the machine, given an L1 and L2, your description should be formal enough that I would immediately be able to construct this machine from the L1 and L2 and your instructions. Does that make sense?
Yeah, I think that's why I was getting tripped
Yeah,
up, because like, how do I like, you know, like define everything in the tuple? Like,
yeah, imagine you're describing a user manual for making this machine, but you don't know what machines your user is going to have on them. You want to describe a general enough how-to guide for anyone who has access to the L1 and L2 to be able to, but assume that your user is stupid. Like, assume your user really just doesn't understand how things work. Yeah.
Okay. Does that also apply for number 1 and number 2?
For number 1 and number 2? Double check them, but I think so.
Because again, they're not giving you like the language. Like, do you have to define the tuple as well?
Yeah, I mean, I think the way to think about this tuple is it's honestly helpful for you to essentially define the tuple. Kind of like how like a cooking guide will have like sections for like what you need and for then prep and then like pre-prep and then this and then that. Treat it as like helping you make sure you didn't forget any details in your instructions, right? You should tell them what the start state should be and how to get it from, you know, whatever they're giving. For the transition functions, you should be able to either say they're identical to the machine or exactly what modifications you're making to them. You know, and this example I think is actually more complicated than problem 3 in some sense. They both have their problem. They both have their issues. So why don't we switch to specifically talking about question 3 for a little bit, and we'll walk through some of the details of the beginning at least, and then we good with this?
Yeah. Wait, I have an idea for problem 3. I just want to like see if.
Let me make sure it's definitely visible on this so that. It's so hard to talk. It's so much more visible on my screen at home than it is on that. But anyways, I think it's fine. I'm gonna erase it.
What are the recordings for?
I upload them on YouTube after my office hours for you guys to reference or for other students to look at.
Cool.
Definitely still worth coming to office hours because questions. The only thing I answer are things that are asked. And also, I think one thing I found the past quarters I've done this is that a lot of the students who seem to find it most useful are the people who came to office hours and they forget something. They're like, you know, it made sense when I was there, but now I'm trying to write it up and it doesn't make sense anymore.
Oh, okay, sounds good.
And then you can look back at the video and be like, oh yeah, I see how that worked. Or if like an exam is coming up and you realize you're weak on something, you can just go back to the office hour from there.
Smart.
And the more questions people come and ask, the more content is in these. So. Whoa. Let's see. So, question 3. Let's just finish it off.
Okay. This is my idea. So we can start by like enumerating, like cat. Like for in the example, like cat and then dog goes in it. So like take every like character of cat like as like as a state and then like make another like machine to see if like from that character you can make the whole like dog like word and then maybe like go back and see if you finish it.
Yes, I think that's a good idea.
Oh, okay.
That's basically the idea.
Oh.
So.
I think I'm gonna
Okay, so yeah, why don't we just use the cat example actually? That's not a bad idea. So I have so much more. This is so much better. It's cat and you can put dog anywhere in it. Is that the machine? Okay. So we have our cat machine, which goes like this, and then let's see. I'm gonna use the assumption that basically if there isn't a transition, I'm not going to draw 26 transitions from each of my things. Assume if it's not the thing I've drawn, it goes to a trap state that doesn't accept. So it just rejects if it doesn't see the transition it needs. Sounds easier than drawing the alphabet. So this is my cat machine, right?
Yeah. Okay,
and this should be an accept state. And we want what type of transition did you want from these to what?
I was thinking like maybe some sort of epsilon transition to see and make a new machine to see
Okay.
like if you can
So let's make our dog machine.
yeah, a dog machine. There we go.
Let's just put it here. I know we don't use this intro arrow, right? But I'm just drawing it for kind of like representing the machine as it originally existed. Okay. And G. Okay. So you want an epsilon transition from every state, right?
Mm-hmm.
Yeah.
To what, the start state?
Yeah.
Like this kind of thing?
Yeah.
Yes. Yeah. Yeah.
Okay. And then you want to do what from the dog machine?
So once you get to the accepting state of the dog machine, go like epsilon back to
Mhm.
where you were, and then see if it finishes, and see if you get a final state in the cat machine.
Okay. This doesn't work. But this is basically what I expect almost every student to first think of.
Oh.
So it's perfect for what I want to go over,
Okay.
I guess I would say. So let's identify, rather than talking about how to fix these problems, because I think we've actually talked about a lot of the ways to fix these problems in the previous example, let's find all the issues with it. Can people find some examples of strings this shouldn't accept that it's accepting right now?
Well, except like cat, dog, cat,
That's true. That's a problem.
or like any.
Yep.
Any like concatenation.
Yep.
Like, oh.
Okay, so that's already an issue. What do we think we can get into a little bit of the problems. I want to find what makes these issues, but I don't want to necessarily identify exactly how to fix them. But let's at least find what the problem is in that. So what creates that problem? Do you think? Like, what do you think is? There's maybe a couple things together that create the problem.
That we epsilon back to the
Yeah.
start of cat.
The epsilon
No
back.
matter where we come from.
Yeah. This is very problematic. This epsilon transition won't work because then you could just keep epsiloning back to your original machine, and you could just do this any number of times. So I want to nix this.
Question: could you maybe like make a new cat machine?
Yes. Exactly.
Oh, a new cat.
Yeah.
Not epsilon
Not.
back.
But what about if every place in cat epsilons to a different dog machine? But then I don't know. Or
No. That's possible. That's fine.
or
You can do that. But let's hold on to that thought for a minute and talk about some other issues of this machine, maybe. So certainly, I could epsilon from this to some new cat machine, which is, we're talking about problem 3. And then there's another issue with that we'll get to in a minute.
Like you don't remember.
You don't know where to start.
You don't know where you are. Yeah. You're epsiloning from here, but you want to go back to what? So if I epsilon from here to the dog machine, I want to go where in my new copy of
the
L1?
next, to the next state in L1, right? You don't want to go back.
Well,
Or do you want to go?
You just want
is
to
you want to go back to where you were.
Yeah. Okay.
Can you just make it like, sorry, like a straight line almost, where you just go back and forth?
No,
No.
because if you can go back and forth, then you can end up with all these weird. So.
Or where you go from, like, at each state of, and sorry if you guys already said this,
no worries.
but, like, for each state of, you make an epsilon transition to A2 at each state of I guess what you're calling the cat machine, but you have to go all the way through the dog machine before you come back to the.
So it looks like you're lining up states of like the cat machine and the dog machine though, but actually every state of cat should map to the beginning of the dog
Yeah,
machine,
exactly.
right?
Yeah.
Okay.
Sorry, this isn't like.
No, it's fine.
States.
But so I'm not totally sure I understand what you're
like,
trying to do.
so if you have
like this is the full box or the full new machine for each of the dog ones.
Mm-hmm.
So you have to go to a start one, and you can only
Yes.
then leave again if you
Yes.
get to a final state.
Yes. But if you're going back to the same machine, you could have this problem where it goes to this cat machine, it goes to this dog machine,
Yeah.
comes back, goes here, and then goes to another dog machine.
Oh yeah. Okay.
Your idea is right though. This idea of making these separate machines is exactly what you need to do. It's
Okay.
honestly one of the hardest parts of the problem. So
Okay.
that's the main idea that people need to figure out. It's good you already know it because that's basically what I was trying to do with the whole last example you missed.
Okay.
So
Cool.
let's see. Okay, so we have that problem if we don't remember where we were. We actually have another problem that I think is probably going to be one of the most commonly deducted points for anyone who gets like close to right, which is we accept one string in particular in this machine right now that we shouldn't.
Oh, is it like two empty, like two starting states or whatever? Actually, no, it doesn't make sense.
We have one starting state right over there in the cat machine, right?
Oh, if it's just dog.
Yeah.
If it's
just
If it's just dog,
Yeah,
that's acceptable.
then
because it epsilons to dog.
so we certainly don't want this to be an accepting state anymore. That's true. We only use the accepting states as a guide as to where to put the epsilons, right? Because if we had a general L2, then we always go to the start state, and the only epsilons out of it come from accept states, right? So we do use the accept states for something, but they shouldn't be accept states anymore in our bigger machine. Does that make sense? Because we don't want to accept in the middle, like
Yeah,
we
what's
want
that
to do
intermediary?
L1, then L2, and then back to finishing L1, right? So we wouldn't want to accept starting L1, seeing L2, and being like, okay, we're done. Because then we don't know if the string completed its L1 thing. So, okay. So that is one problem. There's another problem that I think is actually going to be missed more. There's another thing, like similar problem that we still accept.
Is it like
Just accepting cat.
And so this can't be an accept state anymore, actually. It'll be an accept state in the new copy we make of it, though, right? Because remember, we're not coming back to this machine after we see dog, right? So we don't need it to be an accept state here, right?
Sure.
So we just remove all the accept states from L1, from our first copy of L1, because we don't want to accept before seeing something in L2.
But what if the empty string is in L2?
So if the empty string is in L2, then the first state we go to will be an accept state. And by my definition of L2, every accept state will have an epsilon transition from it back to the state you came from.
Okay.
So you're actually covered, right? Because you would, if the empty string, if this, let's say L2 is now dog and the empty string, then we would also have an epsilon transition from here, right? Back to some, so let's say we go to C and we see C, and then we guess, okay, I think this is when we go to L2, and then we say, okay, I think we saw the empty string already, so now I'm going to go back to your other copy of L1, from going back to where you left from. So it's almost like nothing happened. You just take two epsilon transitions.
Oh, okay. So you're making like another like L1 machine to like remember where you left off, kind of.
So the other L1 machine only exists to A, it means accept states, right? And B, we don't want to create any loops. We don't like this loop.
Yeah.
That's really why we've made that other L1 machine,
Okay,
right?
right.
Yeah. And then that one's going to have accept states, unlike
Yes.
this one.
Yeah.
And then let's see.
How would you keep track of what state you left in the first L1 though? In the second L1.
Right. So you can use the trick you were doing, which is those are separate machines on yours, right?
Yeah.
Right. So they know where you came from.
So like every
But-
like thing in cat has a different dog.
Yes.
Okay.
Yeah.
That's the big one that's going to be the core of the answer to this question.
Wait, but that's what I had,
Yourself.
but then you could still repeat it.
No. But the problem with yours was it goes back to the same L1 machine, right? So yours.
Oh, so you'd have them running like in pair. So then you'd have another like
Yeah.
A1 like that.
And this one
So,
can't
like-
have any accept states, right? Because
Oh.
you need to travel through these first
Okay.
before you accept.
Like that
Yeah.
then,
But if you, yes, exactly.
kind of.
They don't. They'll have accept states somewhere. in them.
But
And they're not. You don't even need separate copies of them. you actually can just have a single A1. Yeah,
right,
yeah.
true.
So
So
you
you
just have one first machine, and then for as many unique
Okay.
strings as you have,
So
you
they
have
all go back.
that many dog and then
Oh,
that
okay,
many
cool.
new.
It's not for every unique string that you have. It's not like the last example in this sense, because
Or but
this
for like every like combination.
for every
like insertion.
for every state you have here.
For every state you have there, you have that many
Dogs.
dogs and
Yeah,
then
yeah.
the second
Yeah.
cat machine.
Because remember, we need to make. You can't count things that are like of undetermined size
Mhm.
in DFAs really well. Like you can't say except everything that has a prime number of ones. It just doesn't work because it can't count, really.
Mhm.
It can either accept some finite number of things, or it can accept like infinitely up as many repetitions of something as you want, but not any particular numbers. Like you can't just pick and choose. So in the other example, we were okay in this because the L1 only accepted a finite number of strings. In this case, all we're trying to keep track of is what state you were in here when you moved to L2, your
Okay.
L2 machine, right? But remember, these are non-deterministic finite automata. They have finite numbers of states. So
Mhm.
this is, you can track this because there are only finitely many states in your machine accepting L1, and so you can make a separate L2 accepting machine for each of them, right? Does that make sense? And then they're going to epsilon back to the other copy of L1, right? To wherever you came from originally to
Yeah.
get to that copy of L2, right? And then there's a couple details like removing these accept states and making them, adding epsilon transitions to them, getting rid of this accept state, things like that. But that's basically the entire answer.
Dang. Okay. I'm surprised I was able to.
The important thing to me is that like, you guys obviously understand answers you write, and that here you are forced to, with assistance, at least make a good number of the intuitive leaps, right? Like I lead you to the place where you have to like figure it out, but I'm still making you guys figure it out, right?
Right.
So
So when the problem says construct an epsilon NFA that accepts it and informally explain how it works. When it says so what do we actually have to?
So informally, like what does it mean to describe informally? Yeah. We went over this just before you got in. No, it's fine. It's not long.
Okay.
I don't mind the videos being semi-inconvenient for people who weren't here.
True.
I'd rather
For real.
it's sort of a thing that actually convinces more people to come. And anyways, the most important thing is that this is helpful for the people who actually took the time to come. What was it? Basically, the way I would describe it is you don't have a copy of L1 and L2. So you cannot formally build this thing. But what you can do is you can write instructions that are so explicit that you assume it's like a cookbook. Like you are giving instructions to someone who is going to have an L1 and L2, or and you don't know what they are, but you can tell them for any L1 and L2 you have, this is how you do this process. And you should assume that the user is an idiot, and this is not a super formal class, so like we're not gonna dock points for missing. We'll dock points for missing important details, but not because your notation's bad or something, and so.
Should we try to construct what, given an A1 and A2, should we try to construct?
You need to construct this A3, let's say.
Yeah.
That's built using A1, A2, and any other instructions you want to give. Like these epsilon transitions aren't part of A1 or A2, but these you can basically describe. Basically, just someone who has these two things should, I don't know exactly where the epsilon transitions will go, but I can tell someone, add an epsilon transition from every state in L1.
Yeah.
That is explicit instructions that if you follow, as long as you follow them, you don't need to be smart, it would work. And so you just need to give some stupid, assumed person these instructions, and they use their L1 and L2 to construct this L3 that will do exactly this.
Okay.
And you don't need to go through the 5 tuple sort of thing. exactly right.
Okay.
Because you can't explicitly build the 5 tuple, but I do recommend still keeping that structure because it will help you not miss details, right?
Okay.
You should still tell them what the start state is. You can even like treat it as like sections of the instruction manual, right? It's like make sure that you have given them the details of how to take, you know, the start states from L1 and L2 and figure out their start state for L3. You know, the transition functions for L1 and L2 and how to construct the transition function for L3, things like that.
So then I guess, like, not necessarily just this problem, I was kind of confused just in general about how to, like...
Sorry, before I move on, I should actually correct something I just said, which is like, I said like use the transition functions from L1 and L2 to describe the transition functions for L3, but notice I'm actually using all the information. I'm using the entire 5 tuple about L1 and L2.
Yeah.
That's all information I can use to construct the transition function for L3, and in fact I need them, right? Because here I use information about accept states, which is a different part of the 5 tuple, to tell you how to make transition functions for L3, right? So, does that make sense? So, you have 2 5 tuples.
Yeah.
Let's say this is the, like, I'm just gonna call it like part 1, 2, 3, 4, 5. These are the various parts of the 5 tuple for L1. I've got another one for L2. And then I want to tell you about L3. Well, in describing like the transition function, I can take information from like, if these are the set of, is the last part of the tuple the set of accept states?
Yeah.
Yeah, okay. So I get like here, the transition function, which is part 3 or part 2 of the description? I don't remember. 3. That's taking information from parts 5 of 1 and 2, right? Because it needs to build the epsilon transitions in this machine, I'm using the information about accept states for these, right? So, I just wanted to like, I didn't want to be unclear, like it's not like you just use this information to build this information.
Can we like draw this like example like in our homework? Like to be like, here's...
You can draw the example,
like,
but it
will
won't...
that help at all? Like,
No. It might help you, which is good enough.
But like if there's like something like unclear, like in the informal or whatever definition we're giving, and then
it might help.
Like would it hurt? I guess
It's not gonna hurt.
Okay.
But it probably will not help much because you just can't draw L1s and L2s that you don't know if like what their structure is at all. You can do things like you draw L1 and then you draw like some accept state that's an abstraction, like a couple accept states like this. So I could draw a bubble that is L1 and make its accept states. Say this is all its accept states. And then draw epsilon transitions from, L2, let's say. So where I want to draw epsilon transitions from all its accept states. Like I could do this kind of thing, which might help you reason about it and make sure you don't miss details, but this is not, I don't think, sufficient for...
Sure.
Like, someone with no level of intelligence with an L1 and L2 can't use this to build it. But I do think, I'm a very visual person, I would not hesitate to draw out, like, this is an explicit example. You can still draw out an abstracted example, right, with things like these ... dots where you just don't know how many there will be. And then just for yourself. And then be like, hey, and then this will, if this came from, let's say this is the start state for it, then if it came from my L1, is going to have states. Some of, same thing. If it came from this one, then when I go back, all these epsilon transitions will go to another copy of L1, right? But they'll go to this state, right? They'll go back to the state they came from, right? So this is like pretty close to the best you can do to draw this, I would say.
Okay.
At this point, right? There's some details I'm missing, but yeah, mostly. Like this will have accept states in here, right? Like steps stay here. Who knows? You know. It's just not enough because it's so abstract. But maybe this gives you a better visual understanding of it. Yeah, I don't know.
Sorry. Go.
I just had a question about problem 1 and 2.
Sure.
Because I'm assuming that they're like less complex than problem 3.
Yeah. Problem 3 is by far the most complicated.
Okay. So they're okay. But my thing is, you also use epsilons to like make new like new machines and stuff, or like how do you like build another machine? Like how do you use a DFA to like create a new machine from another one? I guess. Maybe I'm overthinking it.
That's fine. Let L be a regular language. Show that the language there exists to be. L be a regular language. So U is anything, and then V is from the language. So you can have anything and then okay, that's fine.
It's like the
And you just attach it.
prefixes,
Yep.
right?
Yeah.
And then L2 is all W and L of length n. Okay. W and L such that the length of W is n. Okay. So the first one is not bad at all. Let's see.
Mine's just kind of constructed based off the other one.
Yeah.
So I have like an idea of how to do it, but then the proof that it's regular is kind of getting me.
I think it's like it's regular if you can construct like a finite, right? Doesn't that
So
automatically?
let's.
Like I've got the DFA.
It's not going to be. That thing accepts like arbitrarily long strings, though, right?
Okay.
Because even if, first of all, L might already accept arbitrarily long strings. It might be the language that accepts all strings that only have ones in them, which are arbitrarily long.
Yeah. Okay.
And then this is instantly arbitrarily. Even if L is finite and only accepts the string 1, 1,
Mhm.
that language accepts any string that ends in 1, 1, which is arbitrarily long again.
Yeah.
So that will never accept a finite number of strings. So you
Oh.
can't use any like tricks like I was using before. I mostly just used that to make that example simpler because I started to realize that example is really complicated. I actually don't remember. I assume it has a DFA. Maybe it doesn't. Whatever. If you remove that restriction, I'm not sure. Anyways, so you can use the machine for L, right, in the construction of plus L.
Yeah.
How much more machinery do you guys think you need?
I don't think you need any more. Because at least you need more accepting states. Because at least what I had was if you have W and L, and then you call W X Y.
Mm-hmm.
If there exists like a breakup X Y such that the delta function of Q and Y is included in the final states of L, then Q is included in the final.
This is already way more complicated than it needs to be, I'll tell you.
Okay.
You can add additional machinery other than the machine for L,
Mhm.
and it will make this problem,
Much easier.
yes.
Okay.
You can add very, very, very few states plus the machine for L and be
Yeah.
okay.
Yeah, I just have the machine for L.
Okay. And then what else? But you modified the machine for L?
Yeah.
How?
Essentially, if at any state,
Mm-hmm.
if you have a pathway to reach a final state, then that state is an accepting state.
Yeah, that's one way to do it,
Yeah.
yeah. Yep. That's right.
Okay, I think I just explained it overcomplicated.
Yeah. There's two ways to do it, and that's one of them. Can you use an NFA for this, or was it? Oh, yeah. I mean, you guys know already that things that NFAs accept are regular, right? Or do you not know
But
that yet?
he posted that Piazza thing that said, as far as we know, right now,
NFAs are.
it has to be a DFA.
NFAs.
Oh, it has to
or
be a DFA. Okay, then yes, this is the way to do it.
Okay.
Okay, so if you're anywhere like in L1 and you can get to a final state.
Yeah.
Like just with one character?
No, with
No.
any amount.
So
Oh, okay. Okay, and you can reach a final state with any amount of characters, and then it accepts it.
Yeah.
Okay.
does that make sense? Why though?
Yeah, because it says like there exists something such that you can add, like you can add that to something else and you get something that's accepted by the language. So if you're already somewhere and you add something and it's accepted by L, then it's accepted by plus L.
And the important thing being though that you need to be able to reach an accept state from that state for it to become an accept state. So the sort of trivial way to do this, once you know that NFAs accept regular languages, so you don't know this yet, but can anyone think of how to do this very simply?
Wait, what was
with
the
an
question?
NFA? So let's assume that we now know that everything NFAs accept is regular. How can I build an NFA that accepts this? Because I think it's let me double check that I remember what the language is. I'm doing this right.
It's just the prefixes.
All units such that there exists a v. Yep. Oh, it's prefixes. Oh, never mind. Yeah. No, this is a fine way to do it. I was thinking of the other. So let's reverse it. Let's say everything with the.
Suffix?
Yeah. It's all suffixes. Yeah. If we want to do all suffixes, there's a cute NFA for it.
Do you just like epsilon back or something that like every?
I would do this. It's just I don't want to waste your guys' time on like a stupid exercise, but I just think it's cute. Epsilon transition to the start state of L1. Of L.
Coming from what? Just
This
like
is your
start
this
state?
is your real start
Oh, that's
state.
my start state?
Yeah, this is the start state for L1.
What? Why?
Because it's where all suffixes are in L, right? Like I'm trying to find all the strings such that they are a suffix.
Yeah.
Or such that, wait, what's the way to put this?
Like the end of a word.
I think I'm describing something else actually. Maybe I'm wrong. Let's see. W V. Oh, but the whole thing is in L. Oh,
Yeah.
Never mind. I'm thinking of something else.
So
This more accepts like where you have like a UV and this isn't this by itself is in L and this is nonsense. That's what this is actually
the length
accepting.
is just
Sorry.
the language.
Oh man, I read that.
Right, there's like a new language for everything.
Right.
Like there's L1 where the words are like.
Okay, I misread that problem twice. Ignore my stuff. But yes, yours accepts the question that is actually on there.
Okay.
And the other one is about accepting
Length and.
Length. So can you like
things of length n.
is
Okay.
there can you like keep a counter of like
Oh, I accidentally gave the answer to this already. I just realized.
oops, I didn't hear it.
No. I wasn't talking about problem 2. But I've given the answer already.
The thing with the counter or whatever.
Where have I? There's only one time actually I've talked about length n strings so far.
Oh, because it's finite or something like that.
Yes.
So
So you
How many
enumerate
strings?
all of
Yeah,
them?
this is actually a finite language, right? Because how many strings are there of length n that it could even possibly accept?
What is it like the alphabet to the n or something like that? Because you can like do.
Yeah.
Okay.
Yep.
So
The
like-
alphabet
okay.
to the end.
Ooh, I know stuff. I did not expect that.
So earlier I gave an example of a complicated NFA that involved using the fact that you knew a language was finite, and then just building a DFA that enumerates every possible choice at every step. So instead of having like states that like sometimes have multiple ways to get to them, no, it's
Yeah.
just a tree, and it's of depth n, and then at the end you lead to a trap state that goes nowhere at n plus 1, right? So this, if you have a language L that you know has only accepts finitely many strings,
Yeah.
it must be regular. And here's the proof. Because it's finite, there exists a string of maximum length among all accepting strings.
Yeah.
Right? So now what I can do is I can build a DFA that is a tree. And at every step it has a separate transition and separate state it goes to for all the possible symbols it could read. Like this?
Yeah. Yeah. Okay.
I'm just gonna erase some of this.
So then eventually you get to the one with the max amount.
Yes, and then you make everything along the way that was an accepting string an accept state.
That was an accepting.
Sorry, that was led to by an accepting string, an accept state. So let's say I have A, B, C are my
So
symbols.
like every path that leads to an accepting state becomes an.
Not every path, right? So here, this is we just
isn't there only one path to any given accepting
Yeah.
state?
yes. So there's every state has exactly one way to get to it.
Right.
And so if the only way to get to that state is via an accepting string, then it should be an accept state. Like if the string C is in the language, this needs to be an accept state because there is no other state that you would ever be in
Yeah.
if you've just seen C.
Yeah.
But so by the time you do this n
Mhm.
times,
Mhm.
so let's say n is the maximum length of a string in this finite language,
Yeah.
then once I do this n times, I've enumerated every possibility.
Oh, so then every at that.
Every finite string of
every-
length n has a separate state associated with it, right? And I can just make accept states the ones that are
So if you're like top down, the bottom
Mhm.
level, every single one of those is an accept state.
Yeah.
exactly.
Oh,
So
nice.
for this example, for this question, that's how you do it. But this is actually a more general proof I'm
Yeah.
giving. So
Okay.
question 2 is even easier than what I'm saying. But then what do you do once you're after those accept states? What is their
Then
terms?
you trap them so that they can't go any farther.
Yeah. Yep. And that needs to not be an accept state.
Yeah. So then you
So-
sorry. Go ahead.
So just informally define this again, or do we need to do like
I think
Just like an explanation, right?
yeah.
Okay.
I mean, this is
Really?
what this one can pretty easily be a formal proof in the sense that so let me right now I'll give a formal proof that every finite string is that every finite language is regular because it has a DFA that accepts it. So that's what I was saying here. It's just like I'm giving that proof right now.
Oh, okay.
And that proof is harder and more general than what you need to write. And so basically, right, if I have a finite language, it has a maximum length string it accepts.
Mhm.
Here we actually know it's exactly n, right? But
yeah.
in general, I'm just going to say, let's assume that we're going to call that number n.
Mhm.
Then I'm going to build a tree that at every I'm going to call these depths. So this is like depth 0, this is depth 1, these states are depth 1, et cetera, all the way to depth n plus 1 where the trap state is.
Yeah.
So basically I keep doing this, I keep branching for every possible symbol in the language at from each state. And so there is exactly one state associated with every string of between length 0 and length n. So for every string of length n or less that's in this finite language, I make the state for that string an accept state.
Yeah, so all the ones at length n are
So like
accept states.
So like if length n is 4, let's say that 1 1 1 1 is in the language, 0 1 0 is in the language, 1 is in the language, and that's it. Then there is exactly one state associated with each of these strings.
Yeah.
I make it an accept state.
Okay.
Now my machine accepts exactly the strings that I want and nothing else, right? And so that's it. That's the proof that every finite language is regular. Does that make sense?
Yeah, that I understand.
But for us, we'd only accept 1 1 1 1, right? Because n
Yeah,
is
yeah, yeah.
4.
N's for-
Okay,
Right. So for you guys, what you want to do is you want to take this original language you're given, and you don't want to make everything an accept state at that depth,
Right,
right?
so
It's
anything-
only the things that are in the language.
Yeah, yeah.
So basically, at depth n, right?
Yeah.
Because you're talking,
Oh.
Yeah.
right? So for your question, you're given a language L, but you could just build this tree and say at depth n,
Wait, is everything in the tree not in the language?
yeah. Things that are in the tree are not necessarily in the language.
Okay.
The important
Why is
thing
that?
is I built
Is
so this language. Notice the empty string's not in this language, so this node should not be an accept state.
Okay.
You
I
know.
get it. It's
Yeah,
just
yeah,
how
yeah.
we define.
Right. Oh, sorry. I'm using ABC, but I'm not actually. I gave you a language that isn't in ABC, so let's call it A C B B C C C B. Okay. Right. So none of these should be accept states, right?
Right.
They're in the tree, because putting them in the tree ensures that the only way then to get
Ensures
if I
that something
combine
will-
these
Okay.
if I combine these states, I have a problem because now I can't have a unique way to get to, let's say, a C, right? I need a unique way to get here
Uh-huh.
so that I can ensure that I can make it an accept
Right.
state without accepting any other
Without
strings.
access, got it. Okay.
Yeah, yeah.
Sure. Okay.
But this is definitely formal enough. Of it. The explanation I
I think I was
gave.
thinking of the alphabet. So.
Yeah.
Classic.
But now you see, right? Like you make this
Yes.
tree, it will have a node for every string
Every
up to
unique-
length
yeah.
n.
Yeah.
A
Okay, I
unique
get it,
state
yeah.
for every unique string up to
Uh-huh.
length n, and then you can just circle the ones you want and just leave out the ones you don't and make a trap state at the end.
Fantastic.
And that's the proof that every finite language is regular.
Is that like the language you're using rigorous enough, or do we need to show like?
I think the language I'm using is plenty rigorous.
Oh, okay.
Yeah.
Okay. Cool.
Everything I
Like
thought.
I for
Large
one
tables,
B,
like-
I saw
I know,
like one
same.
page inductions. I accepted some like
Yeah.
4-line inductions, you know, like or like
Oh, wow.
3 lines. Like people
Okay.
just were like inductive step, and they just do like 2 lines, 3 lines of math, and it's sometimes harder to do
Mhm.
that. So like
Yeah.
if you're not
Yeah.
sure, you can always put more detail.
Yeah.
But
Cool.
yeah, as long as you include the important details that show that you have a good
Like, know what you're
grasp of
doing.
exactly why this works,
Mm-hmm. You
you'll
don't
get
have
full
to do
credit.
like if W is in what is it that he was doing? Like if W is in elevate, then like
Yeah, let's
W
do extra.
I
is
was
in L or
looking at the
something.
lectures
That's too
and
much.
Wait, what is this? I don't.
Or like he was like when he was showing before, he was like if W is an elevate, then W is included in L, which is equivalent to of W
Yeah.
is included.
He's writing it in very like formal math
Yeah,
speak, but
okay.
like
Okay.
things can be just as formal in English as they
Yeah.
are in math.
Okay. Cool. Oh, sorry. Just a
No
final
problem.
question. If you
I need to go to time.
Um,
It's fine. Don't worry about it. I'm-
Yeah.
I'll do it
I
right
just
now.
have like trouble for like back at 3 and just in general when we define the transition function, like in class we did the concatenation of 2 languages, and I understand like if Q is in Q1, then it's the set of Q like delta 1s, delta 2s, but like if you're going from one to the next and then back, like Q1, Q2, and then Q1 again, how would you set that up? Like, what's the kind of like process for
No problem. Have a good one.
constructing the delta functions?
I'm not sure exactly what you are asking here.
So, like,
Sorry.
Have the like essentially for problem 3, the idea is you start at A1, then you go to A2, and then you go back to the same state in A1 that you left it at.
Mm-hmm.
But how would you construct your delta function in a similar manner? Or would you? Would it be enough to like explain again as I just let it in words? what
Yeah,
it
yeah.
is?
If you explain it in words, as long as you miss none of the details, that's
Oh,
fine.
okay. We don't have to-
If you are wanting to explicitly build the transition, like
Mhm.
you can't. Let's see. So
Like, this is for the concatenation of A1 and
so Q1 is the states. So
For
Q,
Q1.
if
A1.
Q is in Q1 and transition function according to that, if Q is in Q2, it's fine to just say something has the same
Mhm.
transitions as something else. Like if
Okay.
that's yeah.
Okay, cool.
It'll honestly sometimes be easier for us to read than people
Yeah.
struggling to use
Mm-hmm.
notation they don't understand
Yeah.
completely. But that like
Mhm.
let's see, you could still do it that way though, right? 'Cause
Yeah.
you could say like the transitions. It follows the transitions for Q2 as long for Q2's. Thank you. No problem. As long as it's in, let's say, one of the submachines, one of like dog. Where's this L2 machine?
Yeah.
So, assuming it's in the ith copy of,
Mhm.
you index the copies,
Mm-hmm.
and you say if it's in the ith copy of of your L2 machine, then it follows the transition from it follows the transition function of the L2 machine over the states of the ith indexed version of that machine. Does that make sense? Like that's how I would formalize it, I guess. If you wanted to use the formal notation, you basically have to index your L2 machines and then reference the transition. So you definitely can do it totally formally, and it's not that bad.
Okay.
It's just like you need to come up with some indexing method.
Yeah. Okay.
I would probably have maybe a L1 sub L1 sub 1, L1 sub 2, and then an L2 sub I.
Okay.
For 1 through the number of states, through the number of states of L1.
L1. Yeah.
Yep.
Okay.
And so that's what you're indexing over.
But that's not. We don't have to do that.
Nah.
No. Okay.
As long as you have all of the details of how to construct,
Then it's fine.
from
Okay.
L1 and L2, it's fine.
Nice.
This still involves you, saying how to do these transitions. Like it has the same transitions. All of the indexed copies have the same transitions as L2, and they stay within themselves. Something like that is essentially the same, right?
Yeah, that makes sense.
Okay, let's see. How was the first homework?